Hello, everyone. Today, I present a paper about designing a quality-aware federated learning system with incentive mechanism and model aggregation method. This paper is published in InfoCam conference this year. At first, I will introduce the motivation of the paper. Then I will explain the detail of the quality-aware federated learning system. After that, I will analyze the experimental results, and finally, I will give the conclusions. As we all know, federated learning is a distributed learning framework where all nodes independently train the global model based on local data and send only model updates to the cloud server for aggregation. Since the nodes don't share the local data during the process, the federated learning protects the user privacy to some extent. And the model size is usually much smaller than the training data size. So comparing with the centralized training manner, where all nodes need to send the original data to the cloud server, federated learning reduces the burden of communication networks. Despite the promising metrics of federated learning, technical challenges still exist. The first is that the success of federated learning is highly dependent on node participation. Without the satisfactory rewards, the computing nodes are not willing to participate in federated learning at the cost of computation and transmission resources. And the second is due to various factors, such as training data size or quality and computation capability, the quality of model updates contributed by the nodes varies significantly. It is vital to recruit suitable nodes to participate in federated learning, especially when the recruiting budget is limited. One possible approach is to select as many nodes as possible. However, inclusively aggregating excessive low-quality model updates can deteriorate the global model quality and inflict model convergence problems. Therefore, a quality-aware federated learning system with incentive mechanism is necessary. This is the quality-aware federated learning problem. For each iteration T, given the set of the learning task LT and the learning budget BT, how to allocate the learning task, distribute payments, and aggregate the model updates such that the sum of qualities of all aggregated learning models is maximized. Here, the MT is the learning task allocate result in the iteration T, and SIJT is used to indicate whether the task LJT is allocated to node I in iteration T. And the RT is the payment determination result. This RIJT is the payment reward to recruit nodes I to participate in learning task LJT. The constraint 3 represent that for each learning task, the sum of payments should not exceed the learning budget provided by the task publisher. And the constraint 4 means that each node can only be assigned with learning task that it can participate in. The constraint 5 means that the system limits each node to participate in at most one learning task in every iterations.
So can you go back to the previous slide here? So what do you mean by learning task here?
Learning task means for example, we train two model on dataset MNIST and dataset CIFAR 10. these two model means the two learning tasks.
So you are talking about learning. So each device, they can choose whether they want to participate in a specific learning task. You mean there may be multiple learning problems or learning tasks in the system, not just one federated learning setting.
There are multiple learning tasks in the system. This is the multitask federated learning.
But those multitask, they are independent tasks. I mean, are those learning tasks, they are independent, or they are kind of like more, because of
independent. They are independent. So therefore, each node can only participate one learning task.
In a specific, in a particular iteration T.
Yeah.
So this iteration T here is the time T, or it's more like the, in machine learning, the algorithm is organized into different iterations, right? So is this T the time, or it's actually the algorithm iteration?
This T means the communication run.
Communication, but for example, for different different rounds, we are in different progress, right? Maybe some tasks they have been finished.
Yeah.
Sometimes some tasks they are still ongoing. So in this case, how are you going to define this T and the sets of learning tasks here?
Do you mean it's
Yeah, I mean the so it's easy to understand. For example, if T is the time, okay, so it's basically at this particular time slot, I can choose whether I want to participate into a logistical regression or it's a support factor machine. That's fine. But if you're talking about, this time is the iteration, it's the first iteration of algorithm 1 and also the first iteration of algorithm 2.
I think it's the synchronization for all the tasks.
So it should be so do they, for example, do they have a formula saying that for example, at time T you have a model theta T, then you have T plus 1, you have a model theta T plus 1. Since like, do they have those notation like this in the future?
Yeah,
they have this.
Yes.
So if they have this one, then this is more like the algorithm iteration. It's not the absolute time. But for the algorithm iteration, do they assume that all the tasks they start at the same time? For example, they start from iteration T equal to 0, while you need to decide whether you want to participate into this task or that task. And then next iteration, you also do the same thing.
You can see this constraint, and each node can only participate in one learning task. So if the node participate in the learning task, for example, theta 1, and they will continue this learning task in the following iteration, and it cannot participate in other learning tasks, for example, theta 2.
Oh, okay. So this is a typo, right? They only have LT, right? They don't have the LIT, right?
LIT means the learning task for the node I. And for example, if the learning task LJT is not included in this set, and means the yeah.
So why here they have LT? This is the LIT. Why this one is a LT?
LT is the set of all the LIT.
Oh, okay. But then why?
I think number 4 and number 5, they repeat, right? So you have one constraint would be good enough. You only have number 5 would be good enough, actually. Number 4 is not that necessary.
Yeah, I think so. Yeah, I think there should be something wrong here. Yeah, and the notation here is kind of misleading here.
Yeah, why
this one, right? That's enough.
Why you want to define the condition, following number 4, equation number 4? What do we mean when the learning task is not in that guy's, the specific node's learning task set? What does it mean? I mean, number 5 is easy to understand, right? So one node, one person probably, one device probably can only participate in one learning task, right? That's easy to understand. But what does the number 4 mean?
The constraint 5 means that each node can participate at most one learning task.
Yeah. I understand that one.
And the constraint 4 limited learning task that each node can participate in. For example, there are 3 learning tasks, and for example,
we understand the mathematical language there, but we're trying to say, okay, do they limit the learning task set for each global round for any kind of a particular node or something? Do they put any kind of a limitation on that? For this round, you can only pick up one task from this set, and next round, I give you a different set. Do they specify why we need to put a number 4 there? Because number 5 already say everything. I mean, include number 4.
Oh. I guess according to Maoqiang's explanation before, looks like they may have defined 2 different sets. One is called LT, another one is LIT. So the 4 maybe it means that, well, the LJT must be 0 when when it does not belong to the feasible set.
That's true. That's trying to say, okay, during a specific round, one node can only participate, say, task 1, 2, 3. They cannot participate in task, 4, 5, 6.
Yeah.
Like that. But why that? I mean, so you have any kind of a special spatial constraint or time constraint or whatever constraint, the physical meaning. So one node cannot participate in certain kind of task, but they can participate some other task during some specific rounds, and over rounds they change or something. If you only want to say number 5, I can totally understand, but I don't think number 4 is necessary.
Okay.
Yeah. Oh, by the way, I also have another question. What do you mean by quality aware fair learning problem here? It seems like you try to maximize something like the social welfare, right? So you maximize the sum of the quality of all the learning tasks. So,
in the following, they will give the definition of the quality. It is not the social welfare.
But that's a sum of the loss function, if my understanding is correctly.
You mean here the sum
Yeah.
of the loss function?
Yeah. That's just a sum of the loss function. Or they have the definition of quality.
This is
the definition of the quality function.
Yes, this is the quality function of the
Not only
model
loss function.
aggregation.
Okay.
And yes.
So let's see. Okay. Please move on. Dr. Guo, do you have any further question?
I'm fine. Maybe we can check the details after Maoqiang present the later slides.
Yeah.
Okay. For solving this problem, there are some difficulties. The first difficulty is that the problem is hard to be mathematically externalized because the model aggregation function, because there is a lack of an appropriate metric to quantify the learning qualities. Additionally, the quality of model updates to be uploaded is unknown ahead before learning, which brings challenge to the task allocation. And the second difficulty is it is challenge to allocate multiple learning tasks with both satisfied payments, especially when the learning budget is limited. On the one hand, the nodes have different computation and communication costs, and it is hard to model the learning cost of each participating node. And on the other hand, participants are usually selfish, and they tend to claim a higher cost than the real one in order to increase individual learning profit. And the third difficulty is it is difficult to aggregate the model updates with different learning qualities. To address these issues, the FAIR system, which is the Federated Learning with Quality Awareness system, is proposed. And this system includes 3 parts. It first adopts the loss reduction to quantify the individual learning quality and leverage the historical learning records to predict the current learning quality. And then it models the interaction between the platform and the nodes as a game theoretical reverse auction to cast a quality-aware incentive mechanism. And finally, it devises a model aggregation algorithm to detect outlier model updates and effectively aggregate the qualified model updates to further improve the aggregated model quality. This is the first part, the learning quality estimation. Suppose iteration T start at time Ts and ends at time Te. Participating nodes are required to submit their local model updates at time Tij. And the quantification of the learning quality should reflect how useful that the local model updates can contribute to the global model. Here, they use the loss reduction in each iteration to quantify the training data quality. And then the learning quality depends on both the training data quality and the training data size. The learning quality of one node may change with time, and the recent quality records are more informative than the stale quality records. So here use an exponential forgetting function to weigh the quality records according to their freshness. Here the Q is the quality records, and this parameter is the forgetting factor. So the original problem is transformed into the this learning quality maximization problem. specifically in each iteration T in accordance with the bit information. Here is the bit price. How to select a set of winner nodes, MJT with payments, RJT, for each learning task, such that the sum of the estimated learning qualities of the selected nodes is maximized. The fair system determines the value of the binary variable S for each node and task. If S is 1, the node I will be included into the selected node set, MJT, which means that the learning task LJT will be allocated to the node I. And also the fair system determines the learning reward RIJT in the set RJT for each winner node. The constraints of this problem include all the constraints of the original problem and add a new constraint 12,
Maoqiang, could you
which guarantee.
Yeah, I'm sorry to interrupt. Could you go to previous page? I think the learning quality definition is very important here. I mean, for the rest, probably just you know, the regular mechanism design problem, right? So it's kind of old cliche. Yeah. Training data quality of model I iteration T. What is the TS and TE?
TS is the, for example, TS is the start of this iteration, is the download.
Oh.
This loss J is the download global model, yes. And this loss IJ is the upload the local model loss.
TE is the end, right? TE is the end of this iteration.
Yes, it's the end, yeah.
So loss should be this one is can be negative or is it only positive? MIGT.
MIJT?
Yeah. Reverse loss should be larger than this one. Up this. So
it's positive.
It's positive, right? Okay. Learning quality of node I iteration T. What is the DIJT? DIJT is the data set, data size?
Yeah, DIJT is the data size. So the learning quality depends on both the data quality.
Oh, hey, Maoqiang, why the DIG there is a T? The data set size is different from different iteration.
Yeah. I think it's the sample data size probably. Maoqiang, did you get a Jiahao's question?
I can't hear the before because the never is disconnected.
The question is why do we have the the sub T here? So the data set will be different iteration by iteration. I mean, global round by global round or something.
For this, I'm not sure. I'm not sure the data size will change varies the time. Yeah, the iteration.
Also, do you think this definition is meaningful? Why the quality should be equals to, say, the training data quality times the data size? What's the physical meaning behind this? I mean, physical interpretation or whatever.
I think its original purpose is the if the data quality and the data size is larger, and it will helpful to the global model improvement, but they didn't give the some theoretical proof or yeah.
But when you do the federal learning updates, right? For example, it's federal average. Everybody just submit this one, right? Nobody care about this one.
Yes.
And you aggregate this one and take the average. You aggregate M and take average, right? So I don't know why the quality here, you need to consider the data size. And also, how do you define the eta here, the rho here? So what do you mean by the fading factor? No, forgetting factor.
Because in this system, if you select the nodes before they send up the loss information, so the loss information and training data quality need to be predicted. So they use the historical records, and this factor is the forgetting factor, and the more recent record will be a high factor. And they use.
Okay. What you mean is if it's closer to the converter, its impact will be higher. If it's the initial training, their impact is lower. But how do you define the value of this?
It is between 0 and 1, and this function is, I think, is a common function for the. It's a common function for the forgetting function. Yeah.
It's also very arbitrary, though. I know. So, for example, if we do the privacy preserving machine learning, right? So we define similar decay function or something, follow certain kind of pattern. But you know, it's a kind of a hyper parameter you need to adjust one by one. I mean, for each node, probably that value should be different, right? This value should be different, right? Or
yes, this value should be different.
Or for all the nodes.
And the reason, yes, and the reason is 1, and for remote is the close to the 0.
So do we have to define that as like an exponential function? Can we define like some other function? Is there any explanation for? But the most important thing, I don't understand this one. Why do you define quality like this?
Can I ask a question here? So, I mean, Maoqiang, could you explain what is the loss? I mean, the loss here. Loss mean, do you like the summation or like average for each sample? What's the loss here?
What is the loss here?
Yeah. Do you have an average or just summation?
I think this one is after aggregation from last round.
I know, Doctor, I know the J. I know the model is based on global model, but my question is how do you define this loss? Like a summation for each example or the average of the loss of each data sample?
It's the average of the samples.
So okay, if you use average, so when you times this DIGT, so you becomes a summation of all like summation of local loss. I mean for this node area. Because you have average, you should the summation of all the data samples loss divided by the DIGT. Now you times the DIGT to that. So this kind of quality should be the overall the summation of the loss for each data sample.
Oh, you mean you explain why
Yes, the
they
overall.
need to time the data size. Okay. Yeah, I think you're right.
So why do we need to consider this as a quality? Why don't you try like accuracy?
Can you say?
I mean,
problem
why do you
again?
try the why? I mean, the other question is why don't you try the training accuracy or testing accuracy? I mean, the training accuracy for the local.
Why don't choose the training accuracy?
Yeah,
right?
As a quality metric.
Oh. Maybe it also works. This paper, it choose the loss as the quality.
Okay, I see.
They didn't give the reason.
I think there's a lot of critical point here. So for example, for the loss, you define the MIGT to be the difference of two losses. Well, the first loss, okay. So this one, it's fine. You can get it. You assume that, for example, the server can tell you, well, given this current global model, I know what's the corresponding loss on the testing set. But if you check the second term here, this term, for a single user, how do you calculate the loss here? You don't have the overall test data set, right? You don't have the overall training data set. How do you know the loss after your update? Or are you only talking about your own local objective loss? I assume that you should care about the global objective loss, right?
No, I think they have the God view of everything. That's how to calculate.
Well, if that's the God view, then that's, I mean,
you know all the optimization guy, right? So they always assume the God view of everything.
Yeah, in practice, it's basically like each user, you submit a model update to the server. The server will need to check what's the data quality, right? But the problem is that the federated learning is long ID setting. So how it's very hard for the server to say whether your quality is good or not. It's just because we are literally long ID, right? So
this system in the following day will choose they will choose the direction, the dimension of data distribution more closer to the global data set as the high quality training data. And yes, and they depend on the low quality nodes.
Oh, so basically, if they found that this load, that their data distribution is more similar to the overall distribution, they think they have higher quality, right?
Yeah.
Oh, I see. Okay. But the problem is that you think about the practical case, right? You have four. Let's say you have two overall distribution like this, but then you have four load. Their distribution is like this. But if you aggregate them together, their distribution is in the middle, right? But then you say, oh, their quality, all of their quality, none of them they are good, just because they still, have distance, right? But when they
Yes.
add them together, then you get the middle point. So so this is a heterogeneous, this is a heterogeneous setting because different devices, they have different data distribution. But in this case, well, the data quality here, well, it's not very reasonable to me. So that's, I assume, it's basically like the overall, the benefit, the utility of model update depends on all the local updates from all the, so it's more like it depends on the aggregated result. It does not depend on the individual results. So, but these laws, they define it based on your individual model update. But that's not very easy to define it that way. So that's my question here.
Yeah, yes, I know your problem.
Okay. Yeah, maybe that's because they have they are, as Dr. Pan said, maybe they are more like the mechanical design guy. So they have their own serial to deal with a specific problem.
No, I don't think so. They just try to fit in the mechanism design algorithm. That's their only objective, I believe.
Oh, okay.
You define the learning quality like in this way, estimate learning quality value in this way. You try to fit in the mechanism design algorithm.
Oh, okay. Yeah, maybe they need to be in a specific form in order to use their solution method.
Yeah. Also, for the training data quality, they need some individual value, like the second term, the negative term, so that they can play the selfish game. They can design the incentive compatible mechanism, whatever in the follows, right?
Okay.
So.
Okay. Yeah. You're right. I think that's possible.
Yeah. Well, anyway, Maoqiang, I think that's the key of the paper, right? That's what we call the quality aware. So we need to make sure the quality definition is accurate. But but based on what I heard, at least I'm not convinced. Okay, but anyway, you just go ahead.
Okay. And they add the constraint 12, which guarantees that the payment to each node is larger than its claimed bit price B. And this is the utility function of the node I, which is the difference between the given reward and the learning cost with respect to the computation and energy consumption. And the proposed incentive mechanism need to satisfy the two constraints, which is the truthfulness, which means that for the node I is bit price is equal to the learning cost. If it claims a higher bit price than the learning cost, it is considered as the not truthful. And the second constraint is the individual rationality, which is guaranteed the utility function, utility of the node I is non-negative. This is the algorithm to solve the problem. Clearly, this problem is a multiple knapsack problem, and they use a greedy algorithm to solve it. At first, the algorithm picked the candidate nodes, MJT, that can participate in the learning task LJT. And then the algorithm sort node in descending order by the quality contribution per unit bit. The value is a ranking indicator for node I. And then the algorithm greedily include node I into the winner node set according to its ranking until the total payment exceeds the budget BJT. And the given reward depends on the maximum bid among the winner nodes. And this can guarantee the these two constraints. Finally, the algorithm finds the task with maximum qualities and allocate the task to the obtained winner nodes. And this is the incentive mechanism algorithm. Then is the model aggregation. Unlike the existing model aggregation, for example, Fed average, it proposes a model aggregation consider not only the training data size, but also the training data quality here as the weight. And it's the algorithm. At first, it aggregates the local model updates received from winner nodes using the quality and data science weight, and use cosine similarity to create the similarity between the aggregate model and local model. And then it compute the mean value, the median value, and the standard deviation of the similarity. Since the incentive mechanism eliminates most unreliable nodes before learning, the majority of the received updates should be high quality, and therefore the median can reflect the direction of high quality local model updates. So here it compares the mean value and the median value of similarity to further find out the low quality nodes. The local model updates whose similarity value is smaller or larger than the median value over a preset range will be considered as low quality updates and will be abandoned here. And finally, it will calculate the model aggregation for the remaining nodes.
So, Maoqiang, could you go to Paris 2 page? Previous one. Previous one. One more. So for this one, they try to select the winner nodes, right? So what we call winner node is those nodes satisfying the incentive mechanism constraints to the individual rationale and some budget constraint, some other things, right?
Yes.
So,
yes.
Yeah, truthfulness. Okay. But do they do any kind of design? How do they allocate the reward or something?
Here is the allocated reward, RJT. Yeah, this depends as the smallest k, which is the which depends on the biggest bid price. Bid price of the
I believe this kind of sequential process, right? First of all, you need to determine the winner node set for this round. That's the first step. Next step, then you need to say, okay, I evaluate, the quality of the contribution of different nodes, and I remove low quality nodes and keep high quality nodes. Then after that, I do the aggregation. After aggregations, so I further distributed or allocate the reward to those kind of high quality nodes, right?
Yes.
But during this step, you actually give the reward. I mean, this is should be like a control loop. It's not like this kind of sequential things. How about for those low quality nodes? If they participate, if they're in the winner node set, they participate, right? But later they're going to be removed because of their low quality contribution. Are they going to be rewarded, or they're got nothing?
They can also obtain the reward because this is the incentive mechanism, and they have chosen the winner nodes. And this is only for the model aggregation, and further to remove some low quality nodes. But the reward is given at this in this step.
Yeah, again, it's very confusing. You go to previous slide, number 9. So for this one, again, who's gonna make the decision? I mean, for truthfulness, okay, the server will make all the decision. We'll select the nodes, right? They will design the mechanism to guarantee the truthfulness. Well, how do they design the reward system to guarantee the truthfulness? They use auction.
They have some. They use auction. Yes, use the auction theoretical proof, and
they use a
proof that
they use a second price auction. They use a VCG auction. Or they use a second highest price auction.
It is not the VCG or second bid auction, I think.
So how they use a contract theory? If they use not, they
yes, they use the game theoretical to prove that this reward guarantee these two constraints. And VCG auction is not only this constraint; it has a more constraint. I remember.
But VCG can guarantee incentive compatible or say the truthfulness, right? VCG has a problem definitely, but it guarantees the truthfulness. Yes. Contract theory, if they use that, there should be more design from contract theory part. So I don't know what do they mean by game theory. All these kind of things belong to. I mean, contract theory definitely is part of the game theory, but VCG auction is not. It belongs to auction theory. Well, that's the reason why I don't like this kind of, the appetizer platter things of those Infocom paper. They try to put everything into one part, then it just messed up instead of integrate. You know what I mean?
So this is the way that they make the problem complicated and looks like this will is the review, because if you don't know anything, you want to, oh, this looks fantastic,
Yeah, you're fascinated as a reviewer not familiar with the stuff here, but if you find the reviewer really familiar with everything, then It's very difficult to find a good point of this kind of paper, right? The model is very high level, and all the theory you put there is I don't know. There's a lot. I mean, for each theory, it has a lot of assumptions, right? I don't even know those assumptions will be compatible with each other or not for this kind of a problem.
Yeah, I agree. Yeah, yeah. This is very common in InfoComm.
Yeah. Well, again, for our own student, right? So I just don't. I mean, at least for my group of students, I just don't want you guys just try to, you know, put so many equations there. You don't even know the meaning of the equation, if those equations are compatible with each other or not. It's meaningless. I mean, if for the beginner researcher, if you're doing that, I think that's fine. But you know, after you graduate or kind of, you know, the last few years before your graduation, if you're still doing this kind of research, Maoqiang, I know there's some other guy's paper, but I just don't feel that comfortable with this kind of publication.
Mm-hmm.
Okay. So I believe if I ask further questions, it only makes myself more confusing. Fine, then let's go to the simulation part.
Okay. And in the experiment, they use the 6 model to execute the federated learning on 4 open data sets. And they compare the incentive mechanisms as benchmarks. The first is theoretically optimal mechanism. It adopts the depth-first search approach to find the theoretical optimal solution for the LQM problem, which, however, cannot guarantee the truthfulness of nodes. And the second is the knapsack greedy mechanism. It greedily selects winner nodes based on the amount of training data set.
I still have a question here. What do you mean by theoretical optimal mechanism? For what? Is for the learning, or is it only for the?
For this problem. And
okay.
And it does this greedy algorithm. They directly use some.
For this kind
for example, yes.
For this optimization, right? Okay, okay. Yeah.
And the second incentive mechanism, greedy selects winner nodes based on the data size divided by the bit size, where the data quality and the truthfulness of nodes are not considered. Yes, the first incentive mechanism only find out the optimal nodes depends on this problem, but they don't consider the constraint of the truthfulness and the individual rationality. And the third incentive mechanism is the bid price first mechanism. It selects nodes with the lowest bid price without guarantee the truthfulness of nodes. And in the first experiment, they use this setting, which the n is 20 and the learning task is 1, and this is the bit price distribution, and this is the data size distribution, and this is the nodes, and this is the mislabeled data ratio in the training data set. I will explain this setting in the following, and this is the budget limit. And they compare 4 incentive mechanisms. Clearly, the proposed incentive mechanism can achieve the near optimal performance, and there is a negligible performance degradation when compared with the accuracy result of the theoretical optimal mechanism, and it can outperform the other two mechanisms significantly. And this is the performance of model aggregation. They use the 6 models trained with 4 data sets, and each model is trained with 10 nodes under 4 different scenarios. And the first scenario is the clean data set, which means all distributed nodes have the original data sets to train the model normally. And the second scenario is the noisy label data set, which means there are 5 nodes are clean, but there are 5 nodes which have 50% of the data samples are incorrectly labeled, which means the labels are randomly generated. And this is the error scenario. Among 10 nodes, the training data set of 7 nodes are clean, and the training data set of other 3 nodes are incorrectly labeled. And this is the attack scenario, which means that one of the 10 nodes will submit a random model updates in each iteration, while the others train normally. We can see that the FAIR can outperform the Fed average algorithm in 4 scenarios for almost all models and data set. And the model aggregation performance of the Fed average can deteriorate when degrading the learning quality of model updates. But the FAIR can work robustly under the 4 scenarios. This experiment shows the impact of the data quality, which they fix the data size for each node in each iteration and vary the noise level of the federated nodes from 0% to 100%. The noise level refers to the percentage of nodes within the federated community that has 50% mislabeled data. And they shows that under almost all settings, FAIR can outperform the knapsack greedy mechanism, and the performance gap becomes significantly when the noise level is within the range of 20% and 80%. And although the learning quality decreased with the noise level for both mechanisms, but the performance of FAIR remains stable within the low noise levels.
Hey, Maoqiang, I have a question here. So why there is 4 figures, but in the table there is 3 settings?
These 4 tables
Or 4 figure
means the 4 data set.
Oh, 4 data set. Oh,
yes, 4 different data set. Yes.
That is for the all these 4 is this 4 figure is based on the settings too, right?
Based on the setting 2, yes.
Okay. Also, I have another question is like, for example, for the first figure, when at the beginning the noise level equals 0, these two algorithm, these two strategy like has almost the same accuracy. What's the reason?
They're the same gradient algorithm. The only difference is fair, they consider the quality. For the
Oh, I see.
next step,
Oh, yeah.
they don't consider the quality. That's the reason why later, if your noise level increase, fair will outperform the knapsack gradient.
Yes.
Okay. Thank you.
But if you check the figure, if the noise level go to 100, it doesn't matter the quality, right? So that's what they mean.
100 means that all the nodes have 5% of yes, mislabeled data.
But if you check the figure number 3 from the left to right, I mean, as a 100%, I mean, the knapsack problem gradient and the fair, they're the same. They convert at the same point. What does it mean? It means it doesn't matter the quality. But number 4,
I think when the noise, yeah.
If the noise level is too high, so it doesn't matter the quality or something. No
Yes,
big deal.
it's randomly, yeah.
Yeah, again, go back to the gradient algorithm, they have the.
Yes.
So I think for number 1, number 2, they're different. I don't know.
Because this figure is the CIFAR 10 and this figure is the street number, because these two data sets are more complicated. So these two data set is more easier, I think. So the gap is still exists.
Fine then, yeah. I mean, those simulation figure doesn't deliver any kind of useful information, at least by this page. If you go to the first one, no, the previous one. What's the figure want to show us here? Right, like I said, the theoretical optimal we all understand, right? But why knapsack gradient is lower than the fair only because of the quality design here? If the case, yeah.
Because these two incentive mechanism don't consider the data quality.
That's true.
Yeah.
But if you want to do a fair comparison, you need to do a quality design something with this one, right? So, I mean, at the end of the day, knapsack gradient and your algorithm, they're both gradient. The only difference is you consider the quality design, right?
Yes.
So you can only show, okay, gradient is better than beta price first, or say first price algorithm. We all know that. Gradient work, it's a little bit worse than the theoretical optimal. We all know that, right? The only thing you add here, so okay, I add a pickup mechanism to pick up some good quality nodes. But when I do the comparison, I don't do a fair comparison. I just compare with the traditional, say, gradient algorithm or not that good performance mechanism design. And so, I don't need to see the figure in the simulation. I can get it, definitely, sure, because you consider another factor, right? Another factor related to learning, because the gradient mechanism and the beta price first mechanism, they don't consider anything related to the learning. I mean, all this figure doesn't deliver any kind of useful information. But anyway, fine.
And this shows the impact of learning budget. And there are 100 distributed nodes and four learning tasks in each iteration. Among the 100 nodes, the training data, among the 100 nodes, the training data set of 70 nodes are clean, but the other 30 nodes have noisy training data sets with different levels of data qualities. And we can see that for all mechanisms, the three mechanisms, the learning quality can improve with the learning budget. And FAIR can achieve higher performance under all settings when compared to the other two mechanisms.
Hey, Maoqiang, how do you compute the loss reduction? Reduction in the y-axis. How do you calculate that?
The loss reduction is the loss difference between the two iterations.
Oh, and divide by
the final one. Convert.
Divide by final one.
Yeah.
Okay.
Yes.
Okay, I see. And this is the first time I see a figure like this one to show the advantage, to show the trend. Okay.
Whatever, Maoqiang, I think they should compare with something like robust learning algorithm, right? Because if you consider the noise level or something, if we only compare with those things, definitely kind of outperform them. But yeah, do you have any other figure to show?
No.
Okay, then it's a conclusion, right?
Yes.
Okay.
And here are the conclusions. The authors investigate the quality of where federated learning and where the individual learning quality is estimated. This is crucial, but it's rarely seen in the previous literature. And they propose FAIR to determine the learning task allocation and the corresponding payment and conduct model aggregation in real time. The experiments are carried out to demonstrate the efficacy of FAIR system. That's all. Thank you.
I'm going to stop recording here.